Hey everyone, welcome to our high-level review of a super important concept in chemistry, chemical equilibrium. This is all about the dynamic balance that reactions are constantly trying to find. So let's jump right in. To really get our heads around this, let's start with a simple analogy. Just picture a perfect day at the beach. You've got some people just chilling on the sand, those are our sunbathers, and you've got others cooling off in the ocean. We'll call them our swimmers. Now, check this out. For every single sunbather that decides it's too hot and dashes into the water, one swimmer says, "All right, I'm done," and comes back to the sand. The rate of people going in is exactly the same as the rate of people coming out. So while the number of sunbathers and swimmers stays constant, the actual people are always swapping places. This constant back and forth, well, that's the heart of chemical equilibrium. And that brings us right to the official definition. Equilibrium is simply a state where these opposing processes, people entering and leaving the water in our little story, are happening at the exact same speed. Now, the key word here, and I can't stress this enough, is dynamic. This doesn't mean the action has stopped. It just means it's found a perfect, stable point of balance. Okay, so with that big idea in mind, let's dive into the specific language that chemists use. Getting these terms down is absolutely crucial. So here are our first four key terms. We've got the definition for equilibrium itself, and then we have terms that describe the types of equilibria, like homogeneous, where everything's in the same phase, and heterogeneous, where they're not. But the one to really pay attention to here is the equilibrium constant, K. Think of this value as a special snapshot of the ratio between products and reactants that only happens when the system is perfectly balanced. This is a great spot to hit pause and let these definitions sink in. And here are the next four. Now, a really important distinction to make is between the reaction quotient, Q, and the equilibrium constant, K. Here's the deal. Q is a measure of that product to reactant ratio at any moment in time. K is that special golden value that Q hits only when the reaction is at equilibrium. We also get a little sneak peek of Le Chatelier's principle here, and trust me, that one's a total game changer for predicting how reactions behave. Feel free to pause again and get familiar with these. All right, let's move on to the mathematical tools we use to actually put numbers to these ideas. This is how we go from just talking about balance to actually calculating it. So this is the equation for our reaction quotient, QC. I know it might look a little intimidating, but it's just a simple ratio. Products on top, reactants on the bottom. And those little exponents, they're just the balancing numbers from your chemical equation. All this equation does is give us a snapshot of where the reaction is at any given moment. Are we heavy on products, or do we still have a lot of reactants hanging around? That's the question it answers. And this is where it all clicks into place. When that back and forth, forward and reverse reaction rate becomes equal, the value of Q stops changing. It locks in. And that specific constant value that it settles on, well, that's what we call the equilibrium constant, Kc. So K isn't some new mysterious thing. It's just the special name for Q when a reaction is perfectly in balance. Now, when we're dealing with gases, sometimes it's just easier to work with pressure instead of concentration. But the idea is exactly the same. We set up our ratio, products over reactants, but this time we use their partial pressures. And that gives us QP, the reaction quotient based on pressure. And this cool little equation is like a translator. It lets us convert between the concentration constant, Kc, and the pressure constant, Kp. Here, R is the good old ideal gas constant, T is the temperature in Kelvin, and that delta N is just the change in the total number of moles of gas from your reactants to your products. It's an incredibly handy tool to have. And here they are, all the key equations in one convenient place. This is your whole toolkit for any equilibrium calculation you'll need to do. From finding Q with concentrations or pressures, all the way to converting between Kp and Kc. If you're studying for a test, this is definitely a slide you're going to want to pause and review. So, now that we've got the terms and the equations down, let's just zoom out for a second and see how this all fits together. Here's a quick recap of the whole chapter's flow. You can really see the logic here, right? Section 1 just defines equilibrium. Section 2 gives us the constant, K, so we can put a number to it. Section 3 introduces the amazing Le Chatelier's principle to explain what happens when we mess with that balance. And finally, Section 4 is where we put it all to work with calculations and even connect it back to thermodynamics. Remember, when that Gibbs free energy, or delta G, is 0, that's the universe's way of telling you the system is at equilibrium. Let's just spend another second on Le Chatelier's principle because it is so incredibly powerful. This is the master rule for predicting what a balanced system will do when you poke it. If you add more reactants, the reaction shifts to make more products. If you crank up the pressure, it'll shift to the side with fewer gas molecules. The system will always push back against whatever stress you apply to find its happy place again. So, if there is one single idea that you take away from this entire chapter, I want it to be this. Equilibrium is not some boring, static endpoint where everything stops. It is a constant, vibrant, dynamic balance. It's a state of perfect harmony where the forward and reverse reactions are both still going. They're just happening at the exact same rate. And that leaves us with one last thing to think about. We started with a beach, but this idea is everywhere. It's in economics with supply and demand. It's in ecosystems of predator-prey cycles. It's even in our own bodies, maintaining our blood pH. So my question to you is, where else do you see this elegant, dynamic balance at play in the world around you? Something to chew on. Thanks for tuning in.